Hello and welcome. Today, we are diving headfirst into the world of real numbers. Now, this is a world you probably think you know pretty well, right? Full of your everyday integers and fractions. But it's also home to some truly mysterious characters. And trust me, by the end of this, you are going to see the good old number line in a completely new way.
So, to get started, here's a little puzzle for you. What on earth could possibly connect a perfectly organized military parade with a weird, elusive number like the square root of 5? I know, it sounds kind of crazy, but the answer reveals this beautiful, hidden logic that ties all numbers together. We are definitely going to solve this mystery. First up, let's meet the family. Seriously, instead of thinking about numbers as just a random collection of digits, I want you to picture them as a huge, interconnected family tree. And just like any family, each branch has its own unique story. Okay, so way down at the roots, we've got the natural numbers. The ones you first learned to count with. Simple enough. Then you add 0 to the mix, and boom, you get the whole numbers. Bring in their negative opposites, and now you're dealing with the integers. And from here, the family tree splits into two really big branches. The rationals, which are any numbers you can write as a simple fraction, and their kind of mysterious cousins, the irrationals, which you just can't. The biggest difference between these two branches really comes down to how they behave as decimals. Rational numbers, they're tidy. Their decimals either just stop, like 1/2 is zero point 0.5, or they repeat in a nice, predictable pattern forever. Irrationals, though, they're wild. Their decimals go on for infinity without ever repeating a pattern. This is the fundamental split in our entire number universe.
So, how do we bring some order to this world, especially when it comes to the integers? Well, we start with a golden rule from the ancient Greek mathematician Euclid. He came up with something called a lemma, which is kind of like a mini theorem, a little helping tool to prove a bigger idea. And his division lemma, it's an incredibly powerful rule that basically governs how all integers interact with each other.
Now, I know this looks a bit formal, maybe a little intimidating, but I promise you, it's something you already get from basic division. A is just the number you're dividing, the dividend. B is the divisor. Q is the answer, the quotient. And R is the good old remainder. But the crucial part, the entire secret to this whole thing, is that the remainder R has to be 0 or more, but strictly less than the divisor B. This one simple rule is the key to unlocking some incredible stuff about numbers. So check this out. We can use it to find the highest common factor, or HCF. That's just the biggest number that divides into two other numbers perfectly. To find the HCF of 867 and 225, we just apply the lemma over and over again. See how the remainder from step 1 becomes the new divisor in step 2? We just keep this chain reaction going until that remainder finally hits 0. The very last divisor we used, in this case 51, that's our HCF. It is such an elegant and totally foolproof method. Finding the highest common factor is a pretty neat trick, but what is it actually good for in, the real world? Well, this is exactly where our military parade marches right back into the picture.
So here's the problem. We have two groups of people, one with 616 members and another with 32. They all need to march in the same number of columns. To find the maximum number of columns they can form, we need to find the largest number that divides into both 616 and 32 perfectly. And what do we call that? You got it, the highest common factor. And the answer is 8. If you use Euclid's algorithm, you find the HCF of 616 and 32 is 8. And what that means is they can march in a maximum of 8 columns with perfect rows for both the band and the contingent. That's math in action, creating perfect order. Pretty cool, huh?
Now, this whole idea of a common factor has a famous partner, the least common multiple, or LCM. So while the HCF is the biggest number that divides into two numbers, the LCM is the smallest number that both numbers divide into. They're really just two sides of the same coin, and they're linked by this beautifully balanced and super elegant relationship in number theory.
Okay, let's step away from the nice, orderly world of integers for a minute and jump back into the wild side of the number family, the irrationals. How do we even prove a number like the square root of 5 is irrational? We use this really clever technique called proof by contradiction. Basically, to prove something is true, we start by assuming it's false, and then we see if that leads us to some kind of impossible conclusion. So let's just pretend that the square root of 5 is rational. That means we can write it as a fraction, x over y, where that fraction is in its simplest form. So x and y don't share any common factors. They're co-prime. Okay, if we square both sides, we get 5 equals x squared over y squared, which just means x squared equals 5 times y squared. This tells us that x squared has to be divisible by 5. And if x squared is divisible by 5, well then x itself must be 2. So let's replace x with 5k to show it's a multiple of 5. Now our equation is 5k squared equals 5y squared, which simplifies to y squared equals 5k squared. But wait a second, look, this means y squared is also divisible by 5, which means y is 2. And there it is, that's the contradiction. We started by assuming x and y had no common factors, but our own logic just proved they're both divisible by 5. Our initial assumption created an impossible result, so it has to be false. Therefore, the square root of 5 must be irrational.
So what happens when you start mixing these two types of numbers together? Let's say you take a nice, tidy, rational number, and you add it to one of these wild, irrational ones. What kind of number are you going to get?
The answer is, it is always an irrational number. Adding a rational number to an irrational one can't tame it. The wildness just takes over. The sum inherits that non-repeating, infinite decimal property every single time.
But okay, what if you multiply two irrational numbers together? Does the wildness just get even wilder? And here is where you get a surprising twist. The result can actually be rational. I mean, look at this example. 3 plus the square root of 7 times 3 minus the square root of 7. Both of those are irrational. But when you multiply them out, the square roots just cancel each other out, and you're left with the perfectly rational number 2. So it seems sometimes two irrational wrongs can make a rational right. All right, for our final section, let's look at another secret code hidden inside numbers, this time in their decimal expansions. It turns out you can tell a whole lot about a rational number just by looking at its denominator.
Here is the secret rule. If you want to know if a fraction is going to turn into a decimal that just stops, all you have to do is look at the prime factors of the bottom number, the denominator. If the only prime factors are 2s and 5s, the decimal will terminate. It'll just end. But if there are any other prime factors lurking in there, like a 3, a 7, or an 11, that decimal is going to be non-terminating and will repeat its pattern forever. This rule is basically a shortcut, a total cheat code. So take 17 over 8. The denominator, 8, is just 2 cubed, only a 2, so it terminates. Done. But now look at 64 over 455. The prime factors of its denominator are 5, 7, and 13. And because of that 7 and that 13, it is guaranteed to be a non-terminating, repeating decimal. It's such a simple check that saves you from doing a ton of long division. All right, for our final challenge, let's take a very, very famous rational number, 22 over 7. Using our new rule, what kind of decimal expansion is it going to have? Of course, it's non-terminating and repeating. The denominator is 7, a prime number that isn't a 2 or a 5. And this, right here, is why 22/7 is only an approximation of pi. While 22/7 is rational and its decimals repeat in a pattern, the true value of pi is irrational and its decimals go on forever with no pattern at all. So, from the perfect order of military parades to the elegant chaos of irrational proofs, we've explored the rules that govern this whole family of real numbers. We've seen how every single one, from the simplest integer to the wildest irrational, has its own unique place on the number line. But this leaves us with one final and kind of tantalizing question. What happens when a number isn't on the number line at all? That, my friends, is an adventure for another time.